Okay,
Of course.
I
I
just,
will share my presentation.
Beril, let me introduce you first.
Of course. So sorry.
It's okay. Welcome back, everyone. I hope you enjoyed the networking lounge and the plenary session. We are now in our third session here in the higher education session. We will have two presentations back to back. Actually, they belong to the same project, and the people who are in the project are all here. Beril and Nazmiye are going to be presenting. I am the primary investigator of the project. Burcu Güngör is the researcher in the project. There will be two presentations related to each other. Beril is going to start with the first presentation. Beril, please introduce yourself first, and then we can start with your presentation.
Okay, thank you. Hello everyone. I am Beril Genç. I'm a master's student at Boğaziçi University in Istanbul. I will also share my presentation. I guess you can see my screen. And today I will talk about a training program we designed for pre-service science teachers, a program that combines systems thinking with climate change education. This study is supported by TÜBİTAK, the National Science Council of Turkey. Here's a quick overview of our presentation. First, I will explain why we designed this program. Then I will describe the project, who did it, and what the goals were. After that, I will introduce the participants and give you an overview of the program structure. And then finally, I will share our key findings and conclusion. As you know, climate change is a complex system. It has many variables, many feedback loops, and it affects everything such as society, economy, environment. But teaching complexity is a difficult. First, students and teachers often think about climate change in a simple cause-effect way. They miss the big picture. Second, many teachers don't have the tools or training to teach system thinking. There are gaps in their knowledge of both climate science and pedagogy. Third, the climate change is a socio-scientific issue and it's a controversial. It requires decision making and transferring that complexity to the students is very challenging. So we asked, what can we do about this in a project group? Before I describe the program, let me briefly explain what system thinking is. Yes, we all know what it is, but system thinking means you look at the whole picture and not just one cause and effect, one cause and one effect. You identify feedback loops, reinforcing loops that make things grow, balancing loops that keep things stable. You make complexity using tools like causal loop diagrams and stock flow diagrams. You can leverage points, places where a small change can make differences. And you understand how systems change over time through stocks and flows. There are the core ideas we use in our training program. This is a TÜBİTAK research project. The full title is Designing and Implementing a Climate Change Education Training Program with a System Thinking Approach. Our goal was to help future science teachers understand the climate change as a complex, interconnected system and to give them the tools to teach it that way. The research team includes Gaye Ceyhan as a primary investigator, Burcu Güngör Cabbar as researcher, and myself and Nazmiye Ertuğrul as project assistant. Sorry. And now who participated in this program? The program had two phases. In phase one, the phase training was implemented. 604 pre-service science teachers enrolled the course. 505 completed the sessions and 410 received a certificate. Most participants were third and fourth year students from 7 cities across Turkey. In phase two, the online training part, 130 participants completed the full 8-week program. The majority were female, about 91%, 91.5%. Participants came from 14 cities across Turkey, including some postgrad students. They also wanted to attend the program. The program had 2 phases, as I mentioned before. Phase 1 was a face-to-face training, 2 days, 6 sessions, 12 hours total. It was held on university campuses. The focus was on the foundations of the system thinking and climate change content. We used behavior over time graphs, causal loop diagrams, stock flow diagrams, and Stella Online software. Phase 2 was an 8-week online program. Sessions were synchronous, meaning live and real time, and we used Miro, a collaborative digital whiteboard. The focuses shifted to applying system thinking tools to climate topics through group collaborations and individual reflections. The face-to-face training was organized into 6 sessions, and we start with an introduction to basic concepts firstly. Then we explored population, SDGs, sustainable development goals, and climate. Session 3 look at economy, wealth, and climate dimensions, different dimensions. Sessions 4 focused on the carbon cycle, and session 5 was a world climate simulation game. Participants took on roles and negotiated climate policy. And finally, session 6 was the closing and evaluation all of the program. It was a hands-on and activity-based design from the beginning. This is a screenshot of our Miro board. You can see all 6 weeks of the activities organized in columns. Each week had its own space for group work, individual reflection, and visual tasks. Everything was visible to all participants so they could see each other's work, learn from different approaches, and build on each other's ideas. Here is the week-by-week structure of the online phase. Week 1 and week 2 covered climate change impact analysis. Week 3 focused on system literacy in the curriculum. Week 4 was an introduction to system dynamic tools with practice activities. Week 5 explored climate system components and planetary boundaries. Week 6 covered mitigation and adaptation strategies. Week 7 introduced a climate justice and included a ripple diagram activity. Week 8 used Stella Online for modeling and ended with a program evaluation. Each week combined individual reflection, group collaboration on Miro board, and structured discussion. So for this particular study, we focused on the online phases. We conducted semi-structured interviews with 6 participants after the 8 weeks. We used online open coding and thematic analysis, and we identified 8 themes: prior knowledge, content satisfaction, tools and materials, collaborative learning, perceived outcomes, intention to act, challenges, and suggestions. Let me share the findings. First, what tools did teachers found most useful? Pre-service science teachers finds most useful. Causal loop diagrams, or CLDs, were clearly the favorite. 5 out of 6 participants said causal loop diagrams were the most accessible system thinking tool because it makes relationships visible. You can see how variables are connected, and maybe you don't need much prior experience or knowledge to start using them. And they help you see multiple variable interdependencies clearly. On the other hand, stock flow diagrams were seen as more realistic. They better capture how system behave over time, but they were also more cognitively demanding. Participants say they needed more support and scaffolding to use them confidently. The Stella Online software helped here by letting participants visualize stock flow models interactively. One of the most exciting findings was the shift in thinking we observed. Before the program, most participants had no or little knowledge about the system thinking. They saw climate change as a simple, single cause problem, and they had no specific plan to teach it differently. After the program, participants understood climate change as a multivariable, interconnected system. They plan to bring system thinking tools into their own classrooms. One pre-service teacher actually implemented a causal loop diagram activity with 6th graders during the online training, which was remarkable for us. There were also personal behavior changes. Participants reported becoming more mindful in their daily consumption habits. And now I want to mention about what worked and what didn't work on the Miro, the online whiteboard. Collaborative boards allowed participants to encounter diverse perspectives, and each weekly board felt like a purposeful activity, interactive and engaging, and using real climate scenarios and made abstract system thinking tools feel tangible and applicable. But we have also some challenges. Some participants experienced technical difficulties with Miro board that disrupted real-time integration. Others feel the sessions were too short for deeper exploration. And also we have some suggestions about it. They have some suggestions about it. They wanted to receive materials in advance each week so they could prepare. They suggested that in service teachers, not just pro-service teachers, should be included in the future teacher system thinking programs, training programs. So what are the implications for the science education? First, system thinking training helps teachers move beyond single cause explanations of climate change. It's a fundamental shift in how they conceptualize complex problems. Causal loop diagrams are one of the most accessible entry point to system thinking. They are ideal for initial integration into the teacher education programs, and well-designed online platforms like Miroboard can support collaborative learning effectively. They expose participants to diverse viewpoints and perspectives and encourage their peer interaction. And as a final point, given the strong intention these pre-service science teachers showed, we recommend extending this kind of programs. They recommended this kind of a program to in-service teachers as well. As a final, our research is continuing. I want to add this, and we are still analyzing quantitative pre-post survey data, conducting more qualitative interviews and assessing system thinking skills. As a project group, we are preparing journal articles and conference papers, and also we are presenting at national conferences in Turkey and international ones like NARS and ESERA, and of course at here. To summarize our key message, even a brief system thinking program can change how future teachers see and teach the world. Thank you very much for your attention, and I am happy to take any questions or comments about it. You can also reach us by email. Our contact details are on the slide. Thank you again.
Thank you, Beril. It's great presentation. So if you have any questions, please feel free to write it on the chat. We will get the questions at the end of this session. Nazmiye, it's your turn.
Okay.
Yes,
Can you see me?
we can see your screen.
Hello, everyone. I am Nazmiye. I am a PhD student in Boğaziçi University. I will present our study, which is part of the project that Beril mentioned just now. And the title is Applying Network Analysis to Connection Circles, Examining Pre-Service Teacher Systems Thinking Competencies within Climate Change and SDG 14. Today, the world faces global issues, as you know, such as climate change, pollution, and biodiversity loss. And sustainable developmental goals aims to secure the future of humanity and the planet and ensure prosperity. Education plays a critical role for this issue, and education for sustainable development serves as a means to achieve the 7 SDGs. And system thinking is a promising approach that plays an instrumental role in understanding complexity, and system thinking encompasses a range of skills. These are identifying systems components, understanding interconnections, and feedback nature. So, although studies have examined student systems thinking competency, measuring structural characteristics of students' mental models remains limited. This study addresses that gap by applying network analysis method to connection circles and providing numerical indicators of systems thinking competency. And then our research question is, how does applying network analysis to connection circles contribute to understanding pre-service teacher systems thinking competency in the context of climate change and SDG 14? Our setting and participants, 169 pre-service science teachers enrolled in science education program at 7 universities across Turkey, as you can see here, the universities. And also this table shows the demographic of the participants. Most of them are female students. And the data were collected within the framework of a 12-hour climate change education training program comprising 6 sessions. As you can see, the data was collected in the session 2, which is the SDGs population and climate session. Firstly, connection circle was introduced, and also SDGs were introduced to pre-service teachers. Before data collections, there is a story about cats parachuting into Borneo, and the tool is introduced. Our main data source is this worksheet, which is SDGs and Climate Connection Circle Activity Worksheet. First of all, they answer these 2 questions, and then they develop their connection circles. These 2 questions are preparing questions for developing a connection circle. For the data analysis part, participants generated a total of 230 distinct concepts across all connection circles. These concepts were systematically organized into 25 conceptual categories using this rubric. An example for data analysis, connection circles were digitized and converted into directed weighted network using these 3-column age list format. And these are from 2 concepts we did in this table. And then for the polarity, we identified each polarity. A total of 73 connection circles were collected from participants. Individual connection circles were aggregated into a single collective network to represent the shared mental model of the participant groups. For the data analysis, quantitative network analysis methods, including network density, average path length, modularity, degree distributions, and between centrality were applied to characterize the aggregated network's topological structure and identify central variables within the system. I want to mention about the findings. As you can see, the network representation was created, and the network representation of climate change and SDG 14, life below water. Water drives based on participants generated connection circles presented here. Green's color represents the opposite directions. Red colors represent the same directions, polarities. The thickness of the arrows represent the number of connections applied by participants. And the global climate change and water temperature, this connection was the most connected pair. And also its water temperature and population dynamics is the second one, is the most connected pairs. You can see the summary of network statistics, 23 nodes here, and also 101 ages are here. You can see the degree distributions of degree in and degree out distributions. Degree in, which means that the node out degree distributions range from 0 to 11. The node in degree distribution range from 0 to 13. There is one concept that acts as a hub in the network representation. It's population dynamics, as you can see. 13 other concepts are affected. Also, 11 concepts are affects this population dynamics concepts. And also global climate change and water temperature is other concepts. Also, this figure shows the distribution of between centrality. One variable stands out as an outlier here. Water cycle and physical process has the highest betweenness value. It's followed by salinity and polar fauna. Also, we have feedback loops analysis. According to this analysis, 80 key feedback loops were identified. 5 is reinforcing and 3 is balancing feedback loops. The near equal distribution suggests that pre-service teachers' mental models integrate both amplifying and stabilizing dynamics. The core climate amplification loop between water temperature and global climate change was the most heavily weighted, indicating an emphasis on physical drivers of the climate-ocean system. Population dynamics appears across multiple loops, as you can see here, both reinforcing and balancing, suggesting that this concept may play both driving and regulatory roles in participants' mental models of the system. Also, the split polarity age between population dynamics, as you can see, suggests that participants recognize the complexity of this relationship, though no full consensus was reached and its directionality. And also the presence of trophic, biological, and socioeconomic loops here shows the participants' mental models extend beyond the physical process to human-induced concepts. For the discussion part, pre-service teachers demonstrate an integrated understanding of the climate-ocean system through hub concepts, population dynamics as a hub. The centrality of population dynamics as a hub concepts reflects an integrated understanding of human-nature interactions. The bridging role of the water cycle and physical process further connects biological and physical domains within the climate-ocean system. Cross-domain integration. Water cycle and physical processes acts as the key variable connecting different concept clusters. Some variables like salinity and polar fauna shows teachers conceptualize the systems holistically rather than through isolated disciplinary lenses. Teacher mental models reveal balanced feedback dynamics and complex socio-ecological uncertainties. The loop analysis showed that pre-service teachers' mental models integrate both reinforcing and balancing feedback dynamics in nearly equal proportions. This suggests a nuanced understanding of the climate-ocean system that extends beyond simple cause and effect relationship. The split polarity age between population dynamics and water temperature indicates that full consensus on directionality was not reached. This is consistent with research reporting uncertainty regarding human impacts on environmental systems. Literature shows that applying system dynamics tools within SDG framework enhances teachers' capacity to address complex sustainability issues. So incorporating connection circles is really important as the instructional tools to externalize mental models. Collaborative mapping fosters integrating perspectives. SDG-focused climate change education is really important. Education should emphasize socio-ecological dimensions, particularly the interplay between population dynamics and physical ocean processes, to support complex systems thinking. These are our references. Thank you for your attention.
Thank you, Nazmiye. I think we have 1 minute for question and answers. Any question? Emil, yes, you have a question. You are muted.
Hi,
Yes.
thank you very much for both presentations. Something I found in my work is, at least again with students and in modeling, that even sometimes when you have a feedback loop or a circular kind of mechanism on the surface, when you examine the model, you understand there's not much a lot into the mechanism of what students understand. And again, I understand it's not pre-service teachers. And I wanted to know to what extent did you explore like the mechanisms that they actually understand about climate change? I don't know whether it's an albedo effect reinforcing feedback loop, or perhaps a population dynamics kind of a feedback loop mechanisms that go and affect and impact the climate change, whether they understand even in the perception level why CO2 is actually or other greenhouse gases actually increase the refraction rate of light, of infrared light bouncing back to Earth, those kinds of things.
Do you guys want to answer, or should I go ahead? Okay, I will go ahead. So that's a difficult question, and we are still trying to figure out, and we have a huge data. We have pre-post test implemented systems thinking assessment tool at the beginning and at the end of the session, and we have used different tools to measure students' climate change understanding and systems thinking skill development. So we try to bring them together and to understand the whole picture. And we did that for both face-to-face session and online session, and different participants participated in those two different sessions. So we need to figure out which tools we need to analyze, because we have like connection circles like Nazmiye presented. We have causal loop diagrams that we use another scenario to explain systems thinking and climate change from a different perspective. So we have data, and we are trying to understand the big picture by looking at the pieces.
Thank you. Thanks. That's super interesting.
Thank you. Don, I think you have a question.
Yeah, I'll try to be very quick here. In my experience, it's that people have real difficulty finding the balancing feedback loops, and so I'm really curious why your students have been fairly successful. And one thing I was just wondering about, does it make a difference whether you're studying a system that you're embedded in, if that makes it more difficult to find the balancing feedback loops than if you're studying a system that is somewhat external to yourself? I don't know if you have any other insights into why that might be, but or if you've experienced the same thing. So
it was surprising for us as well to find different balancing and reinforcing loops within the climate system. So we will see what we can find afterwards. We will share the results with you. Okay, I guess we need to move into the other session. That's why I'm
Right.
being rush. So I'm gonna stop recording.